take initiative. And by the way, last time, everything went perfect, except that I forgot to plug in the mic into the computer, so there's a lecture with no sound. Hopefully today it's going to be different. And let me remind you what we did last time. Last time we defined polytopes and tried to define the faces. And there was kind of two different notions of a polytope. One is an H polytope. H polytope is a bounded polyhedron, bounded set of the form P x in R to the D. There are a bunch of affine functions, g1 of x, g sub m of x are non-negative. Each gi is affine. So actually, yeah, this lecture I'm going to write affine functions explicitly. So maybe it's the dot product of x with some vi plus some constant ci. And that's one definition. And for V polytopes, for H polytopes, we actually defined faces. Right? So a face of an H polytope P is a set of the form f sub capital I, which by definition is a collection of all x's in P such that each gi of x is equal to 0 for all I in capital I. That's an example of a face of an, and you get any face of an H polytope this way, maybe non-uniquely if some of the g's are redundant. And we also defined V polytope. As just a convex hull of a finite number of points. Convex hull of V1, V2, V sub n in R to the D. And last time we had some fun trying to guess the definition of a face. Of a V polytope. And yeah, some people actually succeeded in giving the mathematically correct definition of a face, but perhaps nobody said the most convenient one, which I am going to try to present right now. Any questions so far on the previous? All right. So a face of a V polytope, or of any polytope actually, is a set of the form. What you do is you choose some vector h in R to the D, and then you set f sub h to be just the set of all x's in P, such that the dot product of x with h is the maximal possible, equal to the maximum for all points y in P of the dot product of y and h. So the picture is you have a polytope P like this, and then maybe your vector h. Doesn't matter where the origin is. Origin could be somewhere over here. And then you choose some vector h, this, and then you move the orthogonal plane, hyperplane, until it barely intersects your polytope, and then that face is the intersection with that hyperplane is the face called the supportant face for this vector h. And as you kind of let h vary, over all possible directions, it highlights all these different faces and vertices. And if H is 0, you get the whole polytope as a face, etc. Okay. Any questions? And by the way, why is the definition hard to guess? The answer is that because it's not algorithmic, right? This definition here is very combinatorial. You have a finite set of inequalities, you go through all of them, solve a bunch of systems of inequalities and equations, and you're done. Here you have to go through infinitely many vectors, and it's unclear how to program this on a computer. But for us, actually, if we're mathematically, this is very convenient to work with, because you can say, take any vector, and then you can just sort of, it's usually not too hard to figure out what's the maximum, which points of your given combinatorial polytope have the maximum value of some product with some dot product with H. So yeah, that's it. And let me try to give a few examples of faces and establish some terminology. Examples of faces. First of all, as I mentioned, there is the empty face. The face is always there, or the whole polytope P is also a face. So the most important ones for us are going to be the vertices of P, which are denoted, the set of vertices is denoted by vert of P. These are the zero-dimensional faces. Just by definition, it's a face. Last time we defined the dimension of a face as the dimension of the affine hull, right? The minimal affine subspace which contains the face. And so the zero-dimensional ones are the vertices. The one-dimensional ones are the edges. And there's also some faces are called facets. Facets, there's an extra T in there. And facets correspond to codimension 1 faces, where by codimension of a face is just by definition the dimension of P minus the dimension of a face. So in two-dimensional, for three-dimensional polytopes, these are your honest two-dimensional faces. These are the edges, and these are the vertices. But in higher dimensions, there's a whole bunch of stuff in between here. Between edges and face, in facets, there is a lot of things in between. That's that's where your three-dimensional intuition sort of breaks down a little bit. And by the way, so these two faces are usually called trivial or improper, and these, so I'm gonna refer to these faces here as proper faces, which proper means that it's not empty and not the whole polytope. So so far so good. And I decided to actually today I decided to explain some. Yeah, say again. Right, H can be a zero vector, which means that P is the whole thing. Which actually, by the way, from this definition, formally you don't get the empty face. The set is never empty. But yeah, let's include the empty face. So yeah, so today I want to just be a little boring, but try to explain some properties so that later we could use these properties without having to prove them every time. And in particular, so a lot of the things are going to look obvious, but actually are not going to be obvious. And I'm not going to prove them, but it's an exercise which, yeah, it's a very good exercise if you want to develop intuition. So first of all, here is something called the main theorem of polytope theory, which again we're not going to prove, even though it sounds important. I mean, it is important, but so the theorem is that the above two approaches, meaning the polytope approach and this definition of faces and H polytope approach and this definition of faces are equivalent. By that I mean that first of all, each V polytope is an H polytope and vice versa. And second of all, two definitions of faces agree with each other. So no matter how you define your polytope, compute the faces, you get the same set of subsets of your polytope, which, I mean, is very good. It's otherwise, it would have been a horrible, horrible collection of definitions. So yeah, as a proof, the proof takes quite a while, even though it sounds very intuitive, you know, but algorithmically, if you give me a bunch of hyperplanes, let's say, how do I find all these vertices? If you give me vertices, how do I find all these hyperplanes? That requires some work to do. And so the proof is a hard exercise, which you can read in Ziegler. So it requires some tools like the Fourier-Motzkin elimination, things like that. And if you've never seen this before, then it's a good thing to read the first couple of chapters of the book. It's very easy to read and very enjoyable. But in the class, proving all this stuff in class is quite annoying and not too terribly instructive. So that's the main theorem. Question. And from now on, I'm just going to refer to V polytopes and H polytopes as just polytopes. So it's going to be all very nice. And by the way, let me now use the main theorem to actually prove some, well, to not prove, but explain some nice facts about some nice elementary properties. So properties, let me actually view. I got this eraser from Amazon. It's much, much. Properties of polytopes. And the first one I'd like to start with is a little bit, well, it's a new concept. So definition, I'd like to define the Minkowski sum. Suppose you have any two subsets, P and Q, any two subsets of R to D, then their Minkowski sum is the most obvious sum you could imagine. P plus Q is the set of all pairwise sums P plus Q, where little p is in capital P and little q is in capital Q. So that's it. You just sum up all points in this guy plus all points in this guy. And maybe I should give it. So this is going to be important throughout the class. It's going to show up in a whole bunch of places. But for now, let me just give you an example. So maybe I take a horizontal line segment plus a lateral triangle. What am I going to get? Yeah. Okay, that's a good point. So let's see. Does the Minkowski sum change if you translate P or translate Q or both of them? And so let's say I translate P, which, by the way, if you just take a single point, maybe here's your origin, and here is some point C, right, or maybe P, then P plus V plus Q is, you can translate in P by V means taking the Minkowski sum with this point. If I take if Q is a single point, then I just shift all the points of P by this. So if I take P plus V plus Q, it's the same as taking P plus Q plus V, right? Because, I mean, oh yeah, if you rotate P, you get a different, yeah, Minkowski sum is very sensitive to rotating, or even actually rescaling one of the polytopes is gonna give you, in general, the result is gonna be sensitive. It's not like twice P plus Q is some sort of twice the sum of P and Q. That's not true. But this is an important property because what does it mean? It means that in our pictures, we don't have to draw the origin. Because if I want to draw polytopes up to moving them around, up to shift, then this one can have origin over here. This one can have origin over here, or somewhere else. Doesn't matter. They kind of up to an overall shift, the sum is going to be invariant. So what is the sum of, yeah, the trapezoid? Oh, nice. Okay, yeah, that's actually true. Thank you. So and the kind of cute trick that you can use to, I mean, you can actually use this to your advantage, and you can choose the origin to be where it's most convenient. So you can, let's say, choose the origin to be this point here, right? And then every point in the triangle, you just add all these vectors that point to the right. I can draw my triangle again, and then I can draw all these vectors. So the picture I'm going to get is going to look sort of like this. Start here, and if I start here and draw all the vectors, I'm going to get this line segment. So the final picture is a trapezoid. And you can see as you rescale the line segment, the trapezoid is going to be rescaled in these directions. Yeah. Right. Yeah. Here I'm assuming that the line segment is horizontal and this line segment is horizontal. If you try something different, line segment plus, let's say, triangle like this, what do you get? Pentagon. Nice. Again, by the same trick, if you put the origin here, then you get a pentagon, not a regular one, but some sort of right angle. Yeah, so that's the Minkowski sum. And so now you can ask all sorts of questions. What is a face of the Minkowski sum of two polytopes in terms of the faces of? Yeah, let me actually leave the main theorem for now. You can ask all sorts of questions, but the most basic question I want to ask is if question, if P and Q are polytopes, is P plus Q a polytope? What do you think? The answer is yes. Why yes? Oh, okay, right. So here, yeah, that's the first application of the main theorem. If you talk about H polytopes, it's actually sort of hard to prove, to answer this question. But if you use V polytopes, then you know P is, yeah, actually, so let me say the answer is yes, because if P is the convex hull of V1 through Vn and Q, or maybe let me call them P1 through Pn, and Q is the convex hull of convex hull of Q1 through Qm. Then P plus Q is the convex hull of, just take the union of the. Well, no, you actually take Pi plus Qj for all I in bracket n, for all j in bracket m. Does that sound right? Okay. And yeah, again, with the h's, it would have been much harder to do. So Minkowski sum of two polytopes is a polytope. And let me mention some other. Yeah. What's? Oh, you can. I don't know. Yeah, maybe I think that's the connection, because yeah, it sounds like the connection is bad, but it should be visible on the computer. Yeah, let me check. Excuse me. Yeah, on the computer it's fine. Oh, yeah, thanks. Yeah, please let me know if there's any issues. All right, so other properties. Other properties like that. Minkowski sum of two. Yeah, let me actually let P be a polytope. Then, first of all, intersecting a polytope with an affine hyperplane is a polytope. H is an affine hyperplane. Second of all, if you intersect P with another polytope, or actually with another polyhedron, you get a polytope where P prime is a polyhedron. Or maybe you want to project P. A linear projection or affine projection. Affine projection of P is a polytope. All right, which sound like very natural properties that polytopes would have. So how do you prove these? How do you prove the first one? Right. Oh, nice. Thank you. Yeah. If P is an H polytope, then when you intersect with an affine hyperplane, you just add like two new inequalities. So that's also an H polytope. Okay. What about 2? You add more than 2 inequalities. That's correct. But still, this is so these two are easy for H polytopes. And what about this one? An affine projection of P is a polytope. Here it's easier for V polytopes, right? Because if P is the convex hull of a bunch of points, then the projection of P is the convex hull of the projections of the points. Convex hulls are preserved by these affine maps. So yeah, this is easy for V polytopes. Easy. So this is a pretty powerful theorem, right? Which every time you can kind of choose your favorite representation and then use it to prove the stuff that you want to prove. And actually, some natural polytopes that we're going to see today or next time some are going to be given as H polytopes and some given as V polytopes. But before I go on and give you a whole library of examples, let me try to mention a few more properties, I can you can call them obvious properties, even though they look obvious, but they are not obvious properties. And so yeah, I'm going to give you property A, and feel free to use them in the proofs, in the homework if you want. But yeah, I'm going to use them freely. So here's an example of an obvious, which is actually not obvious, property. P is the convex hull of the set of its own vertices. How would you prove something like this? Oh, by the way, do you think it's true, or do you think it sounds true? But yeah, okay. How do you? Yeah. Okay. So the non-vertices don't change the convex hull, which is actually not the definition we used in this lecture, right? In this lecture, vertices are things which maximize like zero-dimensional faces. Face maximizes some linear function, right? So it's not actually, well, that's actually going to be on the list as well, that the different notions of vertices agree with each other. But you're right that so in one direction, right, if you want to say that P contains the convex hull in the set of vertices, then you can just say that the reason is that non-vertices don't change the convex hull according to one of the definitions. What about the other direction? P is going to be a subset of the convex hull. Oh, well, okay, that's true. But why can't P have some other points which don't really belong to the convex hull? Which again depends on the. Well, I guess it depends again on the notion of a vertex, like which one of the which notion are you using? And I guess for some notions it's clear. Yeah, anyways, let me actually try to write down the notions of different notions of vertices. But yeah, anyways, this part is sort of tricky. Yeah. Yeah. Oh, okay. So, all right. So you're asking, can you, if I, right. So, okay, if I give you a polytope, an H polytope, and then I show you a bunch of inequalities, can you tell that these define a vertex or not? That's actually okay. All of these are going to be. Wait, is it not? Oh, okay. Yeah, let me actually. So property B. If P is the convex hull, some points V1, V2, Vn, then it's going to be actually several properties B. Then the vertices of P are among V1, Vn. that's one property, and then V is a vertex. So let's say Vi is a vertex, right? Because it has to be if and only if for some h in R to the d, the dot product of Vi with h is strictly bigger than the dot product of Vj and h, I not equal to j. Which so what is the non-trivial part in this property here? Or is it completely trivial? Okay. What do you mean the right part? Oh, okay. If this part is true, then Vi is a vertex by definition. That's actually not exactly true, right? Because if this is true, then for Vi to be a vertex, you would need that to hold not only for all Vj, but also for all other points in the polytope. Right, right. Okay, yeah. So to go from here to here, you actually need to say some stuff about when you take a convex hull of a bunch of these points, this inequality is still going to be strict if those coefficients are non-zero. Okay. Actually, yeah, that's a good point. So, yeah, let's assume that these are all distinct. Yeah, I mean, I write them as a set. Yeah, let's assume that these are all distinct. Otherwise, you're correct that this is not true. And actually, later for matroids, it's going to be important to allow some of these things to be equal. But for now, for polytopes, let's assume that. And yeah, I guess in this direction it's clear, but in this direction you have to say some stuff about the convex hull. Or yeah, let me mention another characterization. Vertex, that's the one we already mentioned previously. If and only if the convex hull of take all of these V1 through Vn, but without Vi, that and then you get a convex hull that's strictly contained in P. And so that's one thing. And then let me also mention a property B prime, which is that if P is an H polytope, well, let me just write P as given by linear inequalities, x in R to the D, G1 of x, G m of x, minus negative. If it's given in this way, then V is a vertex. So F sub I, which is the set of x's where Gi of x is 0, or I in I, is a vertex. Okay, I think I'm going to run out of space. Is a vertex if and only if and only if what? What is the, well, actually, not if and only, just if. So what would be a sufficient condition for a face like this to be a vertex? Yeah. linear independent. Oh, okay, that's right. So if you want to, each gi is the dot product with some vector. So if those vectors are, they span the whole space, or, I mean, it could be that P has dimension less than Z. Yeah, but that's actually a good condition. That's not the one I'm going to write down. So yeah, let me actually write down the condition, because I think it's actually really convenient to deal with the polytopes we're going to deal with. So this thing is a vertex if you add anything to I, you get empty. You get an empty set. For all j which strictly contain I, f sub j an empty set. So in other words, once you have found the point where a lot of these inequalities are equalities and you can't really make more of them to be equalities, then you get a vertex. Yeah. What if some of the equalities are dependent? Let's say, so that's why it's an if and not an if and only if. So for example, your polytope looks like this. Whoops. This face is G1 equal to 0. This face is G2 equal to 0. And then there's one more redundant face where G3 is equal to 0. And then I can take I to be 1, 2, 3. And then this is going to be f sub I. And then if you add any more G to the set of the ones which vanish at this vertex, then you get an empty set. Yeah? Right. For every, that is also true, right? If you take a vertex and then you take I to be the set of all G's that vanish at this vertex, then this becomes an if and only if. Any more questions on the first A and B properties? All right, then property C. Property C, which is also sometimes it's useful for intuition. So when H is generic, f sub H, remember f sub H is the set of H is the set of all points in P where the dot product is maximized. So if H is generic, right? Let's say you just pick a random vector. Just each coordinate is like phi, and then the next one is E or something like this. How is the phase going to look like? Yeah, actually, it's going to be, yeah, you're right. It's going to be a vertex. And we are going to discuss this later. There's something called the normal fan of a polytope. Yeah, so basically there is some open dense subset of R to the D such that for each vector in there, f sub H is a vertex. And to get a face, you need to choose H that's somehow special. And I mean, I'm not going to prove it because it's not. I haven't even defined what generic means. But yeah, later we're going to discuss this. And actually, here's property D, which is again is going to have a lot of parts. So let's say you have a polytope and then you want to take a face. So what is true for faces of polytopes? Each face f of a polytope P is what? Is a polytope. How do you prove this? Yeah. Oh, right. Okay. Yeah, that's good. Thank you. Right. So each face is obtained from P by intersecting it with some bunch of affine hyperplanes. So we already mentioned that the result is going to be a polytope. Good. Actually, here's another. I mean, these all look very natural. If you want to define a set of, you have this polytope, right? So what are the faces of that polytope? They should somehow be obtained from the faces of P in some way. These are the faces of P. To define what? Yeah, right. Thank you. Which faces of P which are contained in F. And again, this is not non-trivial to prove, right? Because, well, how do you prove something like this? Yeah. Fine. What do you mean by fine? Okay, so you're saying if I take the H representation of my polytope, right? That's good. Yeah. So if P is an H polytope, then it's easy to write down the inequalities for F, and then the faces are given in terms of those inequalities. So yeah, that's actually good. But in terms of V polytopes, again, that's non-trivial. Okay, so you're saying no, because yeah, that's actually a good question. Let me try to. So let's say P is given by G1, etc. Gm is non-negative, and then F is given by G1, etc. Gm non-negative, and some of the i's are equal to 0. Then the face of F would be you set some of these to 0 together with these equal to 0. And that's it, each of those is going to be face of P, and yeah, vice versa. And okay, so in particular, the vertices of F are going to be obtained from the vertices of P by intersecting with F. Right, so that's just a simple consequence of this. Zero-dimensional faces go to zero-dimensional faces. And here's another property. If you take F and you take the affine span of F, how are these two related to each other? Oh, nice. Yeah, intersect the affine span with the whole polytope. So the claim here is that if you have a face, then you don't get any new points in the, if you take the affine span. P cannot look like, a polytope cannot look All right, and here's another property, which, I mean, you can just keep, it's a nice exercise, which I had to do yesterday, which is you just have to write down all the obvious properties you can think of. Intersection of any two faces of P is a face, which, again, you can prove using the H polytope representation, which includes the case you could have two faces which are disjoint. So the intersection could be an empty set, which is a face. And yeah, let me just write down, etc. Here, so there is a whole lot of properties. And actually, these all are, well, most of these are shown in the book, I think section 2 or something like this. So feel free, if you want to just a rigorous proof of all of these, then you should read the book and then let me know if you have any questions on that. But yeah, I'm just going to use them freely and proof of properties A to D. Yeah, and I think next time I'm going to start by actually defining some nice polytopes and trying to study their properties. And I think that's it for today. So thanks a lot for coming. See you on Wednesday.